Fourier decompositions. Fourier decompositions is a subject of applied mathematics that's are huge. Its uses are is huge amount in like physics, electronics and communications, computer science, signal processing like that. So in the motto of this video is that not going to details mathematical point of view. What is this Fourier decompositions? I think if you are a engineering background students in undergrad levels, you have already learned its mathematical formulations. Now the main motto of this video is to give the geometrical intuitions of these Fourier decompositions. In which situations we use this Fourier decompositions technique. This is the main motto of this video. Okay, let's see it. So this Fourier decompositions is a subject in applied mathematics. Applied mathematics, it's a subject in applied mathematics, and it's a huge area. Its applications has it's huge totally, and it's also a very old technique. So in physics they have, in physics, in electronics and communication, in signal processing. So this is also area in applied mathematics, signal processing. As well as in today's now's world, in artificial and intelligence, machine learnings are also used this concept of the Fourier decompositions. Okay, so let's see its geometrical point of view through some examples. Okay, so before starting this thing, we have to know some primary terminology about it. So terminology: what is frequency, what is amplitude, and what is the phase of a Fourier decompositions. So these things first we have to know. First one we have to know what is frequency. Second thing that we have to know, what is its amplitude. And third one is about its phase. But what is these things? So first let's try to understand through an example. Through example, suppose I have taken here some example. The examples is heartbeat. We all of you know that the human heartbeat is the 60 to 100. It's depend on the human to human, but in average it is 60 to 100 beats per minute. We are already known this thing. Beats per minute. So that means what? Means in a minute the human's heart are pumped 60 to 100 times. That is the actually internal meaning of it. So if this thing happen, that means what? That means this 60 to 100 are the oscillation. This is the oscillates. Our heart are oscillates in a minute. Oscillates in a minute. That implies so in a per second, what will be its values? So in a second its value will be 1 to 1.6, like that. 1.6 beat per second. That implies the frequency of our heart is what? The frequency of our heart is 1 to 1.6 hertz. That things are actually called the hertz. That means 1 to 1.6 hertz. Okay. These things are called actually frequency. Means in a second how many times are oscillates. That's the actually internal meaning of the frequency. Okay, I think you all of you understand what is. Now let's try to see it through another examples through this picture. Let's see it. So I am taken this picture from the Wikipedia page. Just search it on Wikipedia. The time series sine wave. Then you can easily find these pictures. I am taking from there. Okay, these pictures for easy of our understanding. So just see it. Here it is a sine wave. Here it is a sine wave. And these things are actually one oscillations of its sine wave. All of you know this is 0 and it is 90 degree. Here in 0 sine carries 0. In 90 degrees value it carries values 1. Again in 180 degree it carries 0. Again 270 it's -1 and 360 0. We have known, and it's called a one oscillations. These things are called a one oscillations, and these are called a sine wave. These are the sine wave. Okay. So in these things are oscillations of a one oscillations. So suppose it's our the time. Its axis is the x-axis is called the time axis. Suppose assume that it's oscillates per second. One oscillate. It's one oscillations in this one. So to oscillates one times it takes 1 second. Let one oscillations takes one oscillation takes 1 second. It's take. That means what? That means its frequency is 1 hertz. That means that. So if it oscillates 2 times, if it's oscillates 2 times in a second, so that means it's 2 oscillations in takes 1 second. So if it takes 2 oscillation if it takes 2 seconds, that means what is its frequency? It will be 1. Sorry, my mistake. Sorry, it's my bad. 1 second, that means its frequency is 2 hertz. Sorry, 2 hertz. That's the, and the magnitude that's seen here, these things are called the amplitude. These things are called the amplitude of this wave. These things are called the amplitude. Okay, these are the, so these times it has taken for one oscillations is taken the time this time, and the frequency is simple. Frequency is 1 by time, or you can tell these things time is equals to 1 by frequency. So these things we can conclude that here from these things are amplitude. These are the amplitude. These value are the amplitude. These are the amplitude of a wave, and the frequency is equals to time period or frequency. These are the time period of a single oscillations. This is the called the time period for a single oscillation. Of a single oscillation, that's period are called. And frequency is equals to 1 by time, simply. Frequency is equals to 1 by time. That is the simple relationship between frequency and time. I think you have already known this. Now let's try to understand the phase. What is phase? I think you have known what is frequency already. What is frequency? What is amplitude? I think you all of you have understand this thing from these pictures. Now let's try to understand what is phase from this picture. What is phase? Let's see it. So here we have seen that there have two graphs. It's a red graph and the red graphs, and one is the blue graph. So there, the red graph is a sine graph actually. These things, if you think these things, it is a sine graph. The seed, its oscillations is one. Its one oscillations is in this time interval. It takes one oscillations from here to here. This in this time interval, it takes one oscillation, and for this blue graph, it's one oscillation time was what? For this blue graph, it's one oscillation takes the time interval in this interrange from here to here. From here to here, in this range, it has taken its one oscillation. So the phase of this graph is called the phase at zero. Just say it. See this red graph first. Just see this red graph first. Here starts from 0 and ends here. So here phase is 0, phase of 0. Okay, here is phase of 0, and phase of the blue curve is this interval. Means I am using here the green color for this interval. This in this range I am talking about, this range. These are the phase of the blue wave. Means blue curve or blue wave as you call. These things are the phase of blue wave, and it's red, and the red wave, in red wave the phase is start here, phase of 0. It's phase of 0. It's phase of 0, and here this in this length is the phase of this blue wave. Okay, I think you all of you understand. Means when it's one oscillation start, this thing, the distance from here to here is called the phase of that wave. That's the thing. Okay, so now let's try to understand through a practical examples why in which situations this kind of pattern we have seen. So just take an example, and just take an example. Suppose we have take the e-commerce website like Amazon's, Flipkart, like that. Somehow e-commerce sells, if you think about like that. E-commerce sells. So if you plot these things through like time, like daily pattern, if you just try to understand the pattern of the sales of any e-commerce website, like daily pattern, they are have a daily pattern, they are have a monthly basis pattern, they are have a annual basis pattern. So if you try to understand this pattern, then you can look like a very beautiful pattern. Okay, suppose let's I first interest to take the daily pattern. What will be the daily pattern? Okay, suppose let's like that. It's the time interval, it is the time, and it is, suppose it's the frequency of this e-commerce sale. Okay, suppose it's in the morning time, it's suppose in the midnight time, it's double. Suppose it better if you take the time. Suppose it's the 12 a.m. 12 a.m. Here some morning time, here 7 a.m. Here some, suppose it's the 12 here, 12 p.m. Here suppose 7 p.m. like that, and again here 12 a.m. like this interval in a 24-hour interval. If you see these things, these pictures, so in 12 there have no so much customers, means there have little amount of customers, those who have interest to buy some things in this period. And after midnight, as time going on, it's laser increased, decreased. And after that, after morning, in morning period, these are increased automatically. It has increased. It has increased, and after some time, and this is the daytime. Daytime it is increased, and after some things, as night progressed, it's closely, and like that means I'm talking about. It's peak time here, and at afternoon something like, and some increased at evening, and after daytime it's decreased again. Again, this type of graph in general we have seen. Okay, actually this when nights increased, means midnight increased, its cell decreased, and after when daytime increased, it's increased, cell increased, and after sometimes it's also there have in afternoon sessions like that, it is decreased, and in evening means when the whose guys are actually jobs in the corporate, they are mainly, we have seen that they are interested to buy their product on evening time, and the sale increased, and after that it is decreased, like this kind of pattern, this kind of actually pattern we have seen. So if you just see these things in the monthly basis, it's the weekly basis. If you see this pattern in weekly basis, and then we can see like that, like this kind of. So this pattern will be weekly basis, the weekend days. So in weekdays it is increased, and in weekend days it is seen that like that it's decreased, and again in weekdays it is increased. Okay, like this kind of pattern. Means in weekend dates, the guys are mainly loves to outside. They are interested to go outside the home, or they are interested to out in the restaurant, like that kind of things. So these patterns is responsible for weekdays on this. These are the responsible patterns for the weekdays, and these are the responsible patterns for weekend days. Weekends. Okay, this kind of. If you see like that, and there have also, if you see these things in a monthly pattern, sorry, annual based pattern. Then like this kind of pictures seen, this kind of pattern you can see. So means in means festival time, means it's depend on the country to country. In suppose if you consider the India, in suppose there have some, in this period there have some festivals like the Sera Diwali. Suppose it's a very famous festival in India, Diwali. And they are in Diwali, they are have also some kind of offers the e-commerce website have given, like Big Billion Day, like Great India Festival, like that, these kind of things. So in generally we have the patterns will be look like this type. It's okay as time progressed, and in Diwali time it's time increased so much, and it's some constant, and they have some little amount, means like they have some, suppose in this period the e-com websites are given some offers, some increased little bit, means this kind of plot in general it is shown. It depends on the situation to situations, problem to problem, time to time. It depends on the various features actually to plot this pattern. Now let's try to understand this pattern. Suppose let's take, somehow we have collecting this data and we got some pattern. Now let's try to understand this Fourier decompositions technique. What is how these things are important to analyze, to featureize this data, this pattern data. It means this time series data, how these things are. Let's try to understand through this example, through this example. It will be better. Just see it. There have the data that we have got, means according to our time. Suppose these are the data that we have got. These are the some time series data. These are some patterns of our data. These are the some patterns of our data. Look like this type of pattern. So suppose you can think this like as a heartbeat pattern or e-commerce, like this kind of pattern. Heartbeat, heart rate, or something like that, that kind of. And these things are called a composite. Just see the pattern of it's not like a sine curve or like a cosine curve or like that a smooth curve. These things are actually called a composite curve, composite pattern. These things are called actually a composite wave or composite pattern. Composite wave or composite pattern, as you like. These things are called. And these things also happen in repeating, like that. Here some oscillations start, and after sometimes it's also repeated somewhere here. I think somewhere it's one oscillations they have given. Somewhere from here it's again oscillated. From here I think it's again oscillated start, something like that. So it's the second thing is that it is the a repeating pattern. It's a repeating pattern. Okay. Now see, now try to understand the geometrical intuitions of this Fourier decomposition. So the Fourier decompositions, if you apply the Fourier decomposition technique on this plot, on these waves, okay, means this is a composite waves, then if you find some kind of beautiful look like this. Actually what happened, the Fourier transformations are helps us to convert this curve is in time domains. It helps us to convert the domain, it helps us to convert the time domain to a frequency domain. So see it in time domain, if you see this curve, it's like a composite curve, it's like a complex curve, complex type of compositions they are have. But if you see this curve in these frequency domains, there have we got a beautiful, very beautiful, these three kind of simple graphs. This is a one kind of sine or cosine curve, like graph. It's and also there have some beautiful oscillations in this interval. Just see it in this interval, there have some oscillations. Sine type of curve. Suppose it's a some curve wave W1. Means they are different. They are either just see this curve. It's a beautiful pattern of this curve, and there have some little bit differences of its frequency, because we have all know frequency is equals to what? 1 by t is equals to frequency. We have known this thing already. Frequency is equals to 1 by t, and here just after applying this Fourier transformations or decompositions on this complex curve, in the frequency domains we got three types of very beautiful pattern curve, like sine and cosine. Suppose let's say W1, let's say W2, let's W3. The main difference of these three curves, they have the three different frequencies. So here just see it. Here frequency is equals to this one, means their frequency is also very large. Here small frequency. Here the same interval, its frequency is 2 times. Here frequency is like, means just see it. Here frequency is small. Here sorry, small. Here frequency is different. So the frequency based on the frequency, so W3 is greater than W2, greater than W1. Okay, these are based on the frequency. These things patterns happen based on the frequency. Now, and they have also different amplitude. Just see it. The height of this curve is denoted the amplitude of this curve. Just see, for W1, this is the responsible for W1, this is responsible for W2, this is responsible for W3. So W amplitude of this W1 graph is little, not much, but amplitude of W2 is high, and as well W3 is also high amplitude. This is the main thing. The beauty of this Fourier decompositions is it helps us to decompose the complex wave or composite wave in a format that in a composite form of different waves that we can easily visualize or easily understand their properties. That's the main concept, the main advantage of this Fourier decompositions. Okay, just see, from this wave we cannot conclude anything, what kind of things is and what kind of properties, but if you just apply the simple Fourier transformations onto it, then we got this kind of beautiful graphs, beautiful waves. That's properties already we have known. What is its amplitude, what is its frequency, just simple the compositions of three waves, its composite wave graphs have occurred. Okay, that's the beauty of the Fourier decompositions. Okay, as when we discuss the case studies, various case studies, then in practically we have seen its application. Okay, I think from these explanations you got the idea. Now let's see, after applying these Fourier transformations, how we will apply these things into featureized sum data. Let's see it. How we will featureize these things. Okay, just see, just take the same examples. So here it is our main this graph, our actual the main graph, composite graph. This is the actual our main graph, and applying the Fourier transpositions onto it, apply the Fourier decompositions or Fourier transformations onto it, then we got like the beautiful graphs like f1 waves. Suppose like f1 waves. Frequency means I am talking about its frequency for this graph W1. Its frequency is f1 and its amplitude, suppose let's its amplitude, this one is a1. Its amplitude is a2. Suppose let's its amplitude is a3. So for W1 graph we got its frequency is a1 and its amplitude is a1. For the W2 wave, it's the wave W1 wave, sorry. For the W1 wave, its frequency is f1 and its amplitude is a1. For W2 wave, its frequency is f2 and its amplitude is a2. For the W3 wave, its frequency is f3, its amplitude is a3. Suppose we got these three after applying the Fourier transformation. Now applying this transformation, these waves, how we'll convert this wave into a new feature data, new features based numerical data. How we'll doing this thing? Let's see it. Okay, this curve that we have seen, these curves are based on the in which domain? Time domain. These curves are in time domain. These curves are in time domain, but after applying the Fourier transformation, the curve that we got, these curves are on the frequency domain. These curves are on the frequency domain. These curves are on the frequency domain. Okay, now see it, how we will apply the features transformations onto it. Suppose we have to construct some vectors for these compositions for this wave. So the vector will be look like this. So first cell will be responsible for the frequency 1, a second cell will be responsible for frequency 2, and third cell is responsible for frequency 3. And here next cell we apply here the amplitude 1, amplitude 2, amplitude 3. These three things, this simple transformation, these simple numerical vectors gives us the features vector of this complex wave. These are the one kind of complex wave. By applying these Fourier transformations, we got these three composite curve. That's frequency and amplitude already we have known. but here we cannot conclude what kind of frequency it's had, what will be its amplitude. But if we apply the Fourier transformations onto it, then we can conclude these things. From this tree graph, we can build our features vector. These are the features vector. Since it's a features vector for each data points, we can easily build for each data points. We can easily find its what will be its feature vector for this graph. It will be on the 6 dimensional, like that, belongs to R6 from here. And since for this complex graph we got this features vector, we can easily apply some of our algorithm, well-known algorithms onto it. Means it can apply the supervised learning algorithms, unsupervised learning algorithm, clustering algorithm, deep learning models, anything, since we have already the numerical features value. So these things, this way, our Fourier transformations helps us to convert some frequency, time frequency data to a features vector. Okay, I think you got the point how these things are applicables. So you conclude these things. So the Fourier representations helps us. So the Fourier representation of a time series data it helps us to featureize this data, to features data on its time series data. It means its time domains. It helps us to featureize this data in frequency domains or repeating waves. That's things always you have to remember. For a repeating wave, waveform, this Fourier representations helps us to convert this time series data into a frequency domain. To convert time series to a frequency domain. And this in frequency domain, it is easy to build our features vector. It will be easy to build our features vector. Okay, that's the simple thing that we have applied. Okay, I think you got the point how these things. If you are interested, please comment below. Then in details, if you don't know it's what kind of mathematical formulations they have for Fourier transformations and what kind of computationals we have used to compute these Fourier decompositions for any signal data, if you are interested, comment below. Then I will make another video for details, clear explanations how these things are actually work. Okay, just I am giving on this, the basis of this lecture is I am giving the intuitions of the Fourier decompositions, how these things are applied on a data sets, and how these things are helps us to convert some data, some complex time series data, to a simple features vector. How these things, how these Fourier decompositions methods helps us to convert some complex time series data to a simple features vector onto it. And after converting these things, we can easily apply some of our machine learning, well-known machine learning algorithms. That's the job actually. The Fourier decompositions helps us. Okay, this is the main important in machine learning. I think you got the idea how these things are helps us to convert some data, to convert some its features data. Okay, so if you have interested, then please comment below. Then I will make another video onto it.